We're going to look at this thing called the definite integral. Starts off with this thing called the fundamental theorem of calculus. Fancy name, but there it is right there. I guess all it's really saying is that, well, it's saying a few things there. It's saying that integration and differentiation are inverse operations, so they cancel out. But let's start. So capital F is representing the primitive function. So if we differentiate the primitive function, then it's the same as differentiating the integral from a to x of function t, and it will end up being function x. This is the key bit. Differentiate the integral of function t to t, you will end up with function x. Because what happens is, you will integrate this and get a primitive function. You will substitute in x, but because you're substituting in x, you've just got function x. Then you would substitute in a, but if you're substituting in a number, you get a constant. Differentiate a constant, you get 0, so you're just left with function x. That's basically what it's saying in a very weird way. Some properties of our integral. Well, that's the idea for our polynomials. Add 1 to the power over the power. Take more note, I guess, with the notation. So, as I mentioned the other day, the long S symbol for integration. So that's our integral symbol. X to the n is called the, you know the name of x to the n? It's the integrand, yeah. So that's the integrand. And when you integrate the integrand, you get the primitive function. So they're the technical terms for those things. Now, so our primitive function, add 1 to the power over the power, you notice I changed to square brackets there, and our limits stay the same. I'm going from a to b. You can factorise, but you can only factorise constants. You cannot factorise the x out of the integral because that's what you're integrating with respect to. And that's what the dx's mean. We're doing this with respect to, in this case, x. But if it's just a constant number, you can pull that out. You can do it a piece at a time. So similar to when we were differentiating. So you don't have to do it all in one hit. You could just do one bit, then do the next bit. Now, this one here. If you want to integrate from a to b, you could integrate from a to c, integrate from c to b, and add the two together. The answer will be positive if the function is positive. So if it's above the x-axis between a and b, then I should get a positive answer. If it's below the axis, I should end up with a negative answer. The value of function x's integral will be less than the value of gx's integral if that's what happens with the curves as well. So you're looking at the two curves on the number plane. If function x is always below g of x, then the answer of their integral should also be in that order. There actually is no reason why the bigger number has to be on top, other than we're just looking at it and we're saying, oh, we're going from a to b. But you could say b to a. But if you swap them round, you need to put a negative sign out the front. Because think about what you're doing. I'm going to substitute in b, then substitute in a. If I decide to do it the other way around, substitute in a minus then substitute in b, I'm going to get the negative of the answer that I actually want. So that's why we need the negative out the front. So swap the values, change the sign. If it happens to be an odd function then, so you have that rotational symmetry about the origin, then the integral from minus a to a must equal 0 because of symmetry. The area below on one side will equal the area above on the other side. One will be negative because it's below the axis, one will be positive because it's above the axis, so add them together, you're going to get 0. If it's an even function, then you'll get twice from 0 to a, because now you have the line symmetry. So the area on the left would be the same as the area on the right. Now that's sometimes handy because 0 is usually an easy number to substitute in, so sometimes we'll do it that way. I remember when you're looking at odd and even functions, if you've got a composite of two or more functions, odd function times odd function will give you an even function. Odd times even will give you odd, and even times even will give you even. Basically, if it's the same type of function, multiply them together, you'll get an even function. If they're different types of functions, then multiply them together, you'll end up with an odd function. Okay, so integral from 1 to 2 of 6x squared. You could, if you wanted to, I mean, it's totally up to you, factorise the 6 out first and then just integrate the x squared, add 1 to the power over the power. Your choice. Some people will leave the 6 in there and then just go, oh, 6 divided by 3 is 2. Doesn't really matter. I mean, you get the same answer. Substitute in the 2, substitute in the 1, and we get an answer. Now, in this case, it's just a number. We're not talking about an area. We're just saying, hey, what's the value of this particular expression? Indices, going to have to change the indices first. So cube root of x is x to the power of a third. Oh, add 1 to a third, you get 4/3, don't you? Right. So you'll get 3/4 because it's 1 over that. So you basically turn the fraction upside down. So we get 3/4 x to the 4/3, and we're substituting 5 to 0. Oh, that's not going to be neat, is it? Cube root of 5. No, you can't do that, can you? So 4/3 is x times the cube root of x. That's not saying x cubed times the square root of x, by the way, make sure. So that's the best we can do because we don't know what the cube root of 5 is. So 15 cube root of 5 over 4. Now, here's one. Hang on, how on earth are we going to integrate sine? We don't know yet. Until you realise, hang on, sine to the power of 5. Sine x is an odd function. So we're saying odd times odd times odd times odd times odd. I think I said that 5 times. Therefore, the overall thing will be odd. You have symmetry from -2 to 2. Therefore, the answer is 0. Now, if you notice things like that, certainly later, once we look at trig integrals and things like this, you can fool a lot of people because they'll go, oh, sine to the power of 5. Okay, what's the technique? I want to integrate sine to the power of 5. Spend a lot of time trying to integrate sine to the power of 5. If you notice the symmetry, you go, oh, well, that's 0. It's an odd function. Now, something like this, you could save yourself some time as well because notice you got the symmetry, -1 to 1. When we're dealing with polynomials, any odd power is an odd function, any even power is an even function. We know the odd functions will be 0. So therefore, I should get exactly the same answer as that. Right? Because the x cubed will go to 0, the x will go to 0, and then for the even part, I can go twice 0 to 1. And so add 1 to the power of the power. Look, how much time does it save us? Not a lot. But I mean, they're things we can use to make our life a little bit easier sometimes. Sketching the signed area function. Okay? Sketching the signed area function. So in other words, the primitive functions, basically. So the area function is the integral from a to x of function t to t. That's the area function. And we know that's going to be function x, where f is the primitive, minus function a. Remember, that's why we started this whole idea of integration. We were solving the problem. We need to come up with a function for the area. Okay. Well, if I wanted to draw it, all I know is the function x. Now, function x, for my sake of my example, looks like it's a quadratic. Now, I've put in some key points here. Now, for the sake of this example, to make life a little bit easier, I am assuming some things here. That the area from 0 to a is going to be the same as the area from a to b, which is going to be the same as the area from b to c, which is going to be the same as area c to d, which I'm calling just capital A. So that bit there is A, down there, that area's A, that area's A, and that's area's A as well. When I draw mine, I like to have them lined up so that I just sort of transfer information up from my other diagram, y up and not down. To get function x, I would differentiate. All right, what do we know? Well, we know area A is equal to 0. Because if I was to integrate from A to A, I'd get function A minus function A, which of course has to be 0. So what does that mean on my graph? So A's got to be an x-intercept. So that's the first bit of information we know. Another thing I now know is that it's a stationary point as well. How do I know that? Remember, this graph here is the derivative, because ax, remember, is the integral of this. So therefore this is the derivative. At a, we're therefore saying the derivative is equal to 0. So I also know there's a stationary point there. What's the value of 0 then? Let's find what that y-intercept, is. So if I was to sub in 0, I'd be integrating from a to 0. A to 0. Well, that would be the negative of 0 to a. And we said that that area value was going to be capital A. So all right, my value for when I substitute an order must therefore be negative A. So on the left, I know it cuts at negative A. Next key point, let's have a look at B. Well, area B would also be negative A. Because I know I'm going from A to B, well, I know the value of that integral will be this area, but it's below the axis, therefore it's negative A. Plot that in. By the way, B would turn out to be a possible point of inflection. Because have a look at it. The second derivative would be equal to the first derivative of this one. So the second derivative of A would equal the first derivative of function x. Well, at B, that first derivative is 0 because I've got a stationary point. Therefore, the second derivative of the curve I'm drawing is 0, and we know they're possible inflection points. Now, when I substitute in C, what do I get? Well, going from A to C, I now have 2A below the axis. So its value must be negative 2A. Let's plot that one. What happens next? Oh, by the way, C is also a stationary point for the same reason as before. Our derivative graph is C, is 0. And area D, so what's D? D is going from A to D. So I've got negative A, another negative A, but now I've got a positive A. All up, I've got negative A. So let's plot that one in. In the interval from C to infinity, area x, AX, not area x, AX is increasing because its derivative will be greater than 0. And if you think about it, it kind of makes sense because if that is a quadratic below, if you integrate a quadratic, what do you get? A cubic. And look what's happened. I've ended up with a cubic. So it's an interesting idea, this sketching the signed area function. There's a few questions in there we'll do to have a go at. But, as I say, normally you start at 0 and it makes life a heck of a lot easier. Alrighty, that'll do us for today.